All right, thank you for your patience. There's a lot going on this morning. I'm not going to be able to do a full class today. Something very urgent came up. And in fact, I'm actually honestly glad that I'm not going to do a full class, not to spend any less time with you, because Zoom just ate my recording from my last class, 2 hours long of a recording that I now have to completely do over. So I'm kind of terrified as to whether that's going to happen again or not. I'm hoping I don't have to do our, 50-minute session that I'm going to be able to handle. But anyway, that's not a problem to y'all. Just like I said, Zoom's eating recordings apparently now. I haven't had that happen since March or April. Either way, I only ever had it happen once before, and a 2-hour one was pretty brutal. So I've been going through my settings and figuring out what the problem was because I didn't change anything. Either way, point being, when you go to YouTube, this video may look a little different if this one gets eaten as well. So that aside, let's get this out. This little joke, haha. Thank you for your patience. So due dates and such, 4.3, 4.4, they're doing the 16th, no surprises there. I'm going to be recording classes. I'm going to be recording Thursday's class. I'm laughing. On Wednesday, pre-recording it, hopefully. I really hope. I'm hoping that this was just a fluke with what happened with my first class, and not what's going to continue to be an issue, because if so, I won't be able to pre-record. Anyways, the plan is that Thursday's class will be pre-recorded tomorrow, roughly the same time, and that tomorrow the video should be uploaded. I just want to make sure everything runs normal. And for today, we're going to be getting into 4.5. Yes. Which is the substitution technique. Four point five, integration by substitution. So we know how to integrate certain functions. In particular, but not limited to, we know how to integrate a power rule, as long as n is not 1. We know how to integrate e to the x and its variations. Again, I'm not writing down every single one. I'm not writing down the answers. I'm just saying what we know how to integrate. We know how to integrate 1 over x, which is when it is, which was the first one, but when it is 1. Let me make sure I give myself lots of space. Pardon me. But we don't have the same basic rules as with derivatives. Products, quotients, etc. There is no product rule. There is no chain rule. There is no quotient rule. Etc., etc. For integration. You can take a derivative of pretty much anything. That's not true of integration, though. The math behind integration is a little weirder. We've already seen how it can be weird, particularly the whole, oh, you can't let the n be -1 in this case because then you end up dividing by 0. So we had this other case that ended up leading to the natural log of an absolute value. So the math behind integration's a little weirder. I mean, just the whole setup, having to integrate infinitely many rectangles using those differentials the dx's and all that stuff. And it gets even weirder when you try and say, oh, well, the product rule is this, the quotient rule is that. Well, no, they really don't exist. When you have a product, instead of having just one flat rule or a formula, you have several different techniques that you would need to try. And even after you try all those techniques, you're not guaranteed an answer. And I will even show you ultimately, not today, an integration that we don't even know how to do as a class. I'm not saying it can't be done. It can be, but you can't do it with any traditional calculus methods. You actually have to use a statistics trick, oddly enough, but not for us. So what do we do? Because we're going to start integrating products and quotients and things that look like chains. Well, our first technique is integration by substitution. So to get around this, option 1, and this is generally written as option 1 because it's the first thing you should probably try, is using a substitution. Sorry, I just keep thinking in the back of my head, man, I hope this records. It's half of what I can think right now, on top of something else going on in my life that is the reason I have to cut class early. Sorry, I'm frazzled. Okay, so option 1 is using a substitution. Now, we've done substitutions before. Back when we wanted to do something, we called it in quadratic form, like factoring x to the 4th plus 3x squared plus 2. We'd call that in quadratic form, and we'd say, let u equal x squared, the middle variable term. After you'd say let u equal the x squared, you'd have to make an extra statement, and you'd say, well, if u is x squared, then u squared is x to the 4th. That way you could transform your variables from x's to u's and get something in a different space, is what we call it, a different variable space, but a lot easier to process. That's what we're trying to do here. We're trying to use some substitution to make something that's ugly, turning into something that's not ugly and is processable with one of our formulas. So, point being, that quadratic substitution thing that I mentioned, there were 2 substitutions, but they kind of one came from the other. That's the same idea here. So this is going to require 2 substitutions. First, we will say u equal, and then whatever, squiggly, squiggly, squiggly. That just means whatever you're going to say let u equal. Maybe it's 2x, maybe it's 5x squared plus 17x minus 3. U equals, then your choice. But it's not really a choice necessarily. By choice, I mean there's really only one good choice. Then take its derivative, but it has to be in this form. Du dx. You have to write it this way. You cannot write u prime. You cannot write f prime. It has to be written as du dx. Just trust me. And this is something that we're going to do over and 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 over. Okay. So take the derivative and multiply both sides by dx. This is an algebraic step that I have referenced before, where the du dx, while it's technically not a fraction, there are a lot of ways that we can treat it as a fraction. Because if this is a fraction, you'd say, oh, the d's cancel. But the d's don't represent a variable. They represent the differential, a small change in the horizontal versus a small change in the vertical. That's what they really represent. So we're going to take this thing du over dx equals, say, 2x maybe, or 2u, or 2z, whatever it might be, and you multiply both sides by dx. So we are going to split up this thing as a fraction. But the du is its own thing, the dx is its own thing. Don't think of the d and the u or the d and the x as separate entities. They're not. Du is thing 1, dx is thing 2. So we're just clearing the fraction, basically. So we multiply both sides by dx. Finally, divide both sides by whatever is next to dx now. So in other words, you have taken what was du over dx and you've solved for dx. That is what we have done. Again, I'm just giving you the steps. We'll apply this very shortly. At this point, we can substitute u and dx into the original integrand, integral, however you want to say it, antiderivative. Now, hopefully, have something that's easy to integrate as long as you only see u's. In other words, no x's. But this is the classic substitution problem. This is the classic, I give you a problem in the dollar, and you find the answer in yen, but I go, no sir, no ma'am, I want the answer as a dollar, you gotta go back. So after integrating, and again, the integration should be simple, go back to x as a variable. Now you don't have to use the letter u, you can use the letter y if you prefer. So then you'd say, we'll let y equals blah, 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 and then its derivative would be dy over dx. And then you'd only see y's when you go to integrate. The reason we like the letter u is the word substitution. Well, the second letter is u. We don't like the letter s because it looks like 5. Excuse me. So example 1. We're not actually going to do any integration here. We're just going to practice the substitution stuff. So find the differential du. Sorry, find the differential, which means the derivative, du, then find dx. That was weird. Why did that go back? And then the third strike is my technology's been a little weird, besides just Zoom not recording. I was using Excel in my last class and it kept, I don't even know how to say it, it just kept messing up really badly. All right, so A. We're going to let u be 5x to the 4th. So our goal is to find the derivative and then break up its differentials, ultimately solving for dx. Our goal is to take this, take its derivative, solve it for dx. We have our let u equals, you take its derivative, and then you solve for dx. Okay. So take the derivative. Du dx. This is a straight up power rule. So drop the 4 out front, so that's 5 times 4 times x to the 3rd, decrease the exponent by 1. You might be saying, well, why aren't you adding 1? Why aren't you dividing by the 5 or the 4 or whatever? Because this is a derivative, not an integral. Here's what's funny. To do some integrations, you have to do a derivative to get to the integration part. 5 times 4 is 20, so we get du over dx is equal to 20 times x to the 3rd. So that's the derivative. Now what I'm going to do is I'm going to take that du over dx equals 20x to the 3rd. And I am trying to solve this thing for dx. It is a thing that is currently in the bottom, which you have been through algebra classes that taught you how to solve for things in a bottom. You clear the fractions and then divide the rest out. So we got to multiply both sides by dx. Actually, I guess this one should just be. There we go. So multiply both sides by dx. That's the step I didn't even ask you to do linear algebra. I told you what to do. Take its derivative, multiply both sides by dx. That's what we just did. We just did this step. Then divide both sides by the thing that's next to the dx. And again, I don't have to tell you this. This is purely Algebra 1, Algebra 2, arguably. So now what we have is the dx's cancel to get du is equal to 20x cubed dx. See, the d's don't cancel. The dx counts as something and the dx counts as something. Those will cancel that way, but it's not just a d canceling with a d. That's not what it is. So now we're trying to solve for dx. How do we solve for something that multiplies? Divide it out. Divide by the 20x cubed. And again, I literally wrote this step. Divide by everything else on its side. So that the 20x cubes cancel there. And what we get is du over 20x to the third is equal to dx. This is the answer for this problem. We have done no actual integrations, excuse me. This isn't a real full problem. This is just practice. All right, let's do another. B. And this one's going to be u equals, let's mix it up a little, e to the 5x, then a minus 7. So let's take its derivative, du dx. E to the 5x, you've got to chain rule that. So it's the derivative of the inside times the whole thing, because it's an exponential. The derivative of an exponential is the derivative of the inside times itself. Old rule. So the derivative of the 5x is the 5, and then you leave the e to the 5x alone. Again, that is an old rule. If you're rusty with it, go practice 20 of them. Go back to the notes. Look at your formulas. The derivative of 7 is 0. It's not minus 7x. Remember, we're doing derivatives. We're going the other way from what we've been doing lately. So the derivative of minus 7 is nothing. This is the derivative. So now what we're going to do is we're going to multiply both sides by dx. There's nothing to clean up. So let's take our du over dx equals 5 e to the 5x. And we multiply both sides by dx to clear the fraction, which will give us du is equal to 5 e to the 5x dx. And then we're solving for dx. That's what we're solving for, so we got to divide everything else out. So we divide both sides by 5 e to the 5x. So that jazz cancels, telling us an answer of du over 5 e to the 5x is equal to dx. These are known as differentials. When you have them separated as a du over here and a dx over there, we start thinking of them more as differentials. Again, we've discussed how dx is the width of those infinitely small rectangles when we talk about integration. When we talk about derivatives, we say that dx is the change in the horizontal position. But the point being that when we talk about a dx, we're talking about something that's going to 0. It's going to be the smallest thing imaginable relative to the du or dy or whatever it is. So again, this is just the substitution part, the second part of the substitution where you figure out what your substitution is, you take its derivative, and you solve for the dx differential. So with that said, let's try out example 2, which will be to find the integrate by substitution. So let's again look at this process as a whole. We'll say let u equal something. I haven't told you what to let u equal, because we're going to do it right and then we're going to do it wrong. So once you figure out what you have your u is, you take its derivative and solve it for dx. Okay, so for a, 2a, we got the integral parentheses x squared plus 3 closed raised to the 4th power times 2x dx. So what we have to do is come up with a substitution, because this is a product. This is like an A times a B. And we said earlier, there is no product rule for integration. Also, it kind of looks like you'd have to chain this. You got an inside bit with an outside bit. Well, there's no chain rule for integration. Fortunately, this is all going to fold into itself with our substitution. So we're going to try a substitution. And I'm going to go ahead and give you a big hint. The substitution is usually the inside or bottom, and possibly just the inside of the bottom. There's no bottom of this, so it's clearly not that. Hint, the substitution is usually the inside. I'll give you a better declaration of that later, but not yet. I don't want to spoil too much of the fun. So what's the inside? Well, the 2x is definitely not that. This looks like the part that has an inside and an outside. The x squared plus 3 being the inside. We've talked about insides and outsides previously for chain ruling. So we're going to say, I don't know why I wrote it over there. Let u equal the inside, the x squared plus 3. So that's the substitution I've chosen to do. So when we say let u be that thing, now we take its derivative. We go du dx. And again, you need to use this notation because you have to see the differentials because you're going to split them up. Well, the derivative of x squared is 2x. The derivative of 3 is nothing. Again, this is a derivative, not an integration. Don't add 1 to the exponents, you're subtracting 1 to the exponents. And then we got to take this thing and we got to solve it for dx, the thing in the bottom. And I will admit this is not the only technique for this. There are other techniques, but unfortunately, they require a little bit more vision, a little bit more forethought. And I don't think that that technique is the best to be doing in an applied calculus class. If this was an advanced, more science-based calculus class, I like that technique. I'm not teaching in here though, because it's more guesswork. This right here, what we're doing is definitive. So we're solving for dx. So, well, first we have to multiply both sides by it. So we have our du over dx equals 2x. We multiply both sides by the dx. Whatever you do to one side, do to the other. That way the dx's are gone on that side. So now what we have is du is equal to 2x dx. Now again, we're trying to solve for the dx. This is what we're trying to solve for because that's what I've suggested so far. We haven't really seen why, but we'll see it soon enough. So we're going to have to divide both sides by the 2x. So that they're gone there. And the dx is now solved for. So I'll leave it in red. Du over 2x is equal to dx. This is a major relationship between how the width is changing in comparison to how the height is changing. So if you know the x value, you can take whatever your change in height is divided by twice your x position, and that's how far the x position should be changing. That's kind of a weird way to think of it. Usually you'd rather want the du to be solved, so your change in height is 2 times the x position times the change in the x. This is a little more sensible, even though you might have a hard time grasping it right now. This has a point, though. So now what are we doing? Where is it up here? At this point, you can substitute u and dx into the original integrand. U and dx. So we're going to write a u wherever you had x squared plus 3 previously, and we're going to write du over 2x wherever we saw dx previously. Those are the things that are getting substituted. So right here, we had x squared plus 3. We don't want that anymore. We now want to write that as a u. And then this dx right here, we don't want that anymore. We want this because that's what dx is equivalent to. Now you might say, well, you're not plugging anything in for the 2x. You are correct. The secondary method I mentioned that's a little more forethought requiring, you just try and manipulate these things to match for the du equals, but they don't always match and the manipulation can be tough. But by solving for dx here, this 2x, or at least the x, should go away. At the end of this next step, there should be no more x's. That is the whole point. You can have numbers, you can have u's, but you can't have x's anymore. We're going from the dollar to only seeing yen, and the dollar is the x, the u is the yen. So let me undo all those little circles I had. Okay. So now our integral. I'll write this out. The integral of x squared plus 3 raised to the 4th times 2x, missed my x, dx. This will become the integral of, instead of writing x squared plus 3, we write u. Again, this x squared plus 3 is u, so write it as a u. But it has a 4th power, so don't forget that. So the 4th is still there, times the 2x is still there, but I'm replacing the dx. The dx is really this, du over 2x. So times du over 2x. This is important because we still have a differential, and now the differential is in our new variable. You can't have a bunch of x's here and then a u here, or a bunch of u's here and an x here. We're only supposed to have a single variable for integration, ... for now. So what happens? Well, we can clean this up. The u to the 4th is just a u to the 4th. But look at this 2x right here, and this 2x right here, they're identical, top and bottom. They cancel. Gone, gone. Now again, the 2's don't necessarily have to go. What's absolutely important is that the x's are gone, and all you have are u's and du's. So this is now just the integration of u to the 4th du. Look how simple that is in comparison to the original problem. It looks like a D4. I'm going to fix that. But just look at the comparison of those two examples. They're mind-blowingly different. Oh, that's even worse. Maybe not worse, but there we go. My D is ugly. I'm hyper-focused right now, sorry. So there we go. The integration of u to the 4th times du. Well, that's just a straight up power rule. So we add 1 and divide by the same. Now remember, when you integrate, you don't use this symbol anymore. You don't leave the du anymore. All that stuff is gone. When you go to apply your formulas, u to the 4th changes to u to the 5th. Divide by 5. This is an integration. You're adding 1 and dividing by that number, not bringing the exponent down and decreasing it by 1. So in this integration problem, you had to do a derivative and an integral. This is one of my favorite styles of problems because of that. It puts everything all together in one nice, neat package. And if you box this up, first of all, you're wrong because there were no upper and lower limits, so you got to have your plus c. Second of all, I gave you a problem in dollars, and if you give me this as your answer, that's in yen. I don't want the answer in yen. I want it in dollars. So we have to go back to x. How do we go back to x? Well, instead of writing u, we write what u is equivalent to. We said u is equivalent to x squared plus 3. We made that choice. We made it based on the problem, but we made a choice. So when all is said and done, this is now equal to the integral of, instead of writing u to the fifth, it's this thing to the fifth. So we'll need a parentheses. X squared plus 3 raised to the fifth power all over 5. What did I do wrong? I did it intentionally. That's right. I left my integration symbol. See, I deleted it here and I brought it back here. It's very easy to just think that's going to be in the answer. So we got to start over. No integration symbol. It's just the u to the fifth should be x squared plus 3 raised to the fifth all over the 5, then plus c. This is the answer in all its glory. Or if you like your fractions separated, 1/5 parentheses x squared plus 3 to the fifth, then your plus c. That would also be acceptable. I think the first version looks a little prettier, so that's how I usually do it. But there's nothing wrong with the second version, so you do you. Again, this is a lovely problem because it involves both of the major techniques we focus on in this course. Limits were important to getting to derivatives, and limits are important for going to an integration because you make those triangles, you take the limit as the width goes to 0. But we really don't focus on the limit aspect so much as the application of the formulas of integration and derivation, differentiation. So this was the correct substitution. Let's do this problem again, but let's see what happens with a wrong substitution. So why is it important to do this? Well, maybe when you're taking a test or doing a homework problem, you make a wrong substitution. How can you tell it's wrong? Remember, the main point was to get this right here, an integration with no x's. You got to be completely in your new chosen variable. So let's go back to the original problem, x squared plus 3 raised to the fourth times 2x dx. So instead of letting it be the inside, let's let it be this thing to the side. So let's say I said, let u equal 2x. Now, another substitution you might say is let u be the x squared plus 3 to the fourth. First of all, it's generally not that complicated. It's usually not the inside and the outer exponent. So that's just a big spoiler for you. But again, there is a third substitution that you could try that would fail. I'm just doing the second one. If u is 2x, when you take its derivative, it's just 2. You're going to multiply both sides by dx. Excuse me. Which will give you du equals 2 dx. You will divide both sides by 2 to solve for the dx. So you get du over 2 is equal to dx. Okay, so our integration of x squared plus 3 raised to the fourth times 2x dx is going to become, well, the first bit, this x squared plus 3, I didn't see anything about that over there, so we have to leave it alone, including its fourth power. U, we said, was 2x, so this thing right here, that's going to be our u. So that's times a u. And then the dx we just said is over here. Dx is now du over 2. So this is times du over 2. All right, well, that 2 doesn't cancel like it did in the last example. That's not a problem, though. Again, just constants aren't really issues. It's the variables. You have x's in here and a u and a du out here. There's no way to proceed with this. there's still mixed variables and absolutely no way to get rid of them right now. So this is how you can tell that you've gone wrong on your substitution process. And again, my major hint was that your substitution is usually the inside of something or the bottom of something, or if the bottom has an exponent, the inside of the bottom. I'm not telling you it's that way every time. There are more complicated problems in the world. What I'm telling you is that's what we usually see. All right. With that being said, let's do one more of these, and that might be all the time we have, given my emergency situation. So let's do the integration of x to the 4th plus 5 raised to the 8th power times x cubed dx. So again, this looks like a product rule. It could look like a quotient rule. We'll see. We will see an example of that next class. But it looks like a product rule, and there's no product rule integration formula. Not for us. We have methods for them. The first being this substitution technique. Another technique is known as integration by parts, and it'll be a minute before we get to that. And by minute, I'm exaggerating. So when we look at this, you go, all right, well, Mr. Beckner said the substitution is usually the inside. This is the inside, so that's probably what the substitution is. Now, what you might accidentally do is just say, let it be the part that's the x to the 4th. That's not going to be good enough. You will actually get something that only has u's. But the integration will still have what looks like a chain rule effect, and it won't be good enough. So let's say let u not be just the x to the 4th. It needs to be the x to the 4th plus 5. Try out just having it be x to the 4th. You won't get the same answer. So we take that and we take its derivative. So du over dx is equal to, not 3, excuse me, I'm talking and writing at different speeds. 4x to the 3rd would be the derivative of the x to the 4th. Derivative of 5 is nothing. And then we take this bad boy and we solve it for dx. So du over dx equals 4x cubed. Same 2 steps every time pretty much. Multiply by dx so that those cancel, giving us du equals 4x cubed dx. Divide both sides by the stuff that's not dx on its side. 4x cubed, 4x cubed, so that those cancel, giving us du over 4x cubed is equal to dx. So again, in terms of what's important for the substitution, it's the let statement. We're going to rewrite the x to the 4th plus 5 as a u, and the dx statement. So our original integral, x to the 4th plus 5 raised to the 8th times x cubed dx. This will become the integral of, instead of writing x to the 4th plus 5, I'm going to write u. But we leave the exponent of an 8 there. The x cubed after that is also going to stay. And you're like, oh, we're mixing variables here, but just hold on a second. Now the dx gets replaced. The dx is du over 4x cubed. So times du over 4x to the 3rd. Bad looking x, just fixing that. There we go. And look at this. We have an x to the 3rd in the top. We have an x to the 3rd in the bottom. The x to the 3rds cancel. I don't want to show the crossing out this time. I want to leave that there. So this becomes the integral of u to the 8th times du. The u to the 8th is in the top, the du is in the top. This 4 is still here. It's in the bottom, though, so make sure you put it in a bottom. This no longer has any x's. That means we have done an appropriate substitution. When you integrate u to the 8th, you get u to the 9th over 9. So this would be u to the 9th. When we integrate, we're adding 1 for power rules over 9. But then there's that times 1/4. Now, you might not put the 1 there. You may just leave the 4 in the bottom. It's up to you. And then you have your plus c. But this 4 was in a denominator, so it needs to be in a denominator somewhere as a product. What some people may have done is taken the 4 out, like this. 1/4 integral of u to the 8th du, which would give us 1/4 times u to the 9th over 9 plus c. The same thing, just in a different order. The 4s and the 9s are in the bottom, so you can multiply them to get 36. So that's 1 over 36 times u to the 9th, or u to the 9th in the top, and 36 in the bottom, plus c. Well, we have to go back to x. Instead of writing u, we write x to the 4th plus 5, because that's what u is equivalent to. That's what we said. So instead of u to the 9th, it's now x to the 4th plus 5 raised to the 9th over 36 plus c. And there are a couple different algebraic ways to write that, but that's, in my opinion, the best. And if you don't trust this, you can take the derivative of the answer, and you should get the original problem. You will need the chain rule, because these have insides and outsides. Insides and outsides, that's pretty typical when you integrate by substitution. You usually get something that if you were going to take the derivative of this, you'd have to chain it. It's kind of interesting in that manner. If you took the derivative of this, the 9 would go out front, the 9 would reduce it to 36 and give you a 4 in the bottom. This would be raised to the 8th power, but then you got to multiply by the derivative of the inside. The derivative of x to the 4th plus 5 is 4x to the 3rd. That 4 would cancel with the 4 that's in the bottom, and you have your x to the 3rd to the side. It does, in fact, work. What I think is super interesting about this process is that's too low. There we go. If you try to do the integral of x to the 4th plus 5 raised to the 8th power, this can't be done this way or any easier way. What I think is interesting about this is, what am I missing? What's different about this versus the original problem? The original problem had this x cubed in it. It actually made it look worse. With that x to the 3rd, you go, oh man, that looks way uglier. It looks like a product rule. This doesn't look like a product rule. This should be easy. Actually, no. That's what is really, really funny about this, is that you need that x cubed there, because in this substitution process, you end up with an x cubed in the bottom of your dx that will cancel it. Because when you go to try and do a substitution here, you'll still have that x cubed in the bottom, but it's not going to cancel with an x cubed in this top. Now you've got an x cubed in the bottom and a u in the top, and you can't integrate it. What you would actually have to do with this problem is take that binomial and multiply it by itself 8 times, which is probably going to take you like 30 minutes to do, and then use the power rule. Again, the point being, the uglier problems are often actually easier to do than their simpler looking counterparts. So again, I'm not saying this can't be done. I'm saying it can't be done this way. I mean, that would be a lot of products to have to do. A lot of products. Oh man, I'm telling you, 30 minutes, I might actually being generous there. It might be 40 minutes for you. I don't know. It might be. It depends on how quick you can go, but it's a lot of bookkeeping. How are we on time? It's also important that this x cubed is x cubed, and it's not an x squared, and it's not an x to the fourth. There's a relationship between this and this when you're dealing with polynomials. Notice that this was an x to the fourth, and this was an x to the third. That relationship right there, the fact that they're one off from each other, is important because when you do the derivative of the inside ends up bleeding to an x to the third, you end up dividing it to a bottom, and that's how we end up matching that power and canceling it. So let's say this number right here, let's say this was a 7, you couldn't do it as a substitution. Let's say it was a 6, you couldn't do it as a substitution. Let's say it was a 2, you couldn't do it as a substitution. When you're dealing with polynomial terms, and this is critical, the biggest exponent inside and the exponent outside, generally speaking, need to be one off from each other. This needs to be one less than the other. That way the derivative part will cancel it. Go back to example A. Look at this. This was an x squared, and then this was an x. It has nothing to do with the outer exponent. The outer exponent is not consequential to the substitution. But this was a 2 and this was a 1. In other words, if this was, say, a 7 right here, I would need this to be an x to the 6th. Now, if there's extra terms and extra variables, that could complicate things, or they could be set up nice and pretty, which I'll have an example of for next class. So what I'd like you to do for now is, before we, yeah, I don't know that I have enough time to do this one because I need to be out the door in 5 minutes. Think about this. The integral, one of these is going to be example C. The integral of x e to the x squared dx. Now, the fact that the x is in the front instead of the back like the last two, that doesn't matter. If you think you need to put the x after the e to the x squared, that's okay, but it really doesn't matter that it's in front if this is the proper one, versus the integral of e to the x squared dx. One of these you can evaluate, the other you cannot, using this technique. And in fact, the other one is very similar to that thing I mentioned, needing a statistics trick. Maybe there's a negative involved, maybe there's a half involved. It has to do with something called the normal distribution. But that's not anything we're doing in here, so don't worry about that. But just using those first two examples, I'm not going to assign the homework for this section officially yet because we're not even close to being done. But try and do these on your own using a substitution. And I hope it's obvious which one actually works. And I really tried to hammer that out with an example earlier. You know, if the x cubed was here or if it wasn't here, what's the cause and effect? So I am very sorry that I have to cut this class so short. I am also really hoping that this thing records. I am crossing my fingers so hard because I have to go redo that 2-hour class. I don't want to have to redo this one. I really don't. So now I'm not redoing that yet. I got to redo that later today. But that's not y'all's problem. Hopefully it won't be your problem. Hopefully this goes and records. So have a good one. Remember, I should be recording this tomorrow from like 11 to 1, as long as what's going on today does not remain an issue. I'm really knocking on wood over this one. Sorry, it's been an interesting summer. I think y'all can understand. There's a lot going on for all of us, which is why I try and be really lenient with y'all with these multiple days to test, with the 2 attempts. My life's pretty crazy. I imagine yours is equally as crazy. So I'm trying to be as fair as possible. And I hope you feel that way. Y'all have been kicking butt so far. Thank you for dealing with this issue. I'm sorry to cut the hour, but it is what it is. I will quote, see you tomorrow/Thursday, and then I will be back to regular recording time Tuesday at 11. But again, there will be a lecture posted for your Thursday class. Don't worry. And hopefully it'll be a full 2 hours or an hour and a half, something like that. All right. Take it easy. Email me if you have any questions. Please record.